So let's have a look at these, and then we're going to do some synthesis, most of today. So the first one, you are looking at an atom with a lone pair, which means this is a resonance donor. And an OP director. But you're also looking at an electronegative element that has a dipole with a negative charge on the oxygen and a positive charge on the carbon. This is inductively electron withdrawing. So the effect of the resonance is to activate the ortho and the para positions, but the effect of the inductive electron withdrawing group is to somewhat deactivate the ortho position relative to the para position. So the major product is going to be bromination in the para position. It's possible to brominate additionally. It's a strong enough activating group. You can actually put a second bromine on the ortho position if you have multiple equivalents of bromine. But you can get it to stop at 1 with 1 equivalent of bromine. You will get some ortho, but not as much ortho as you might think. So that's the major product. Inductively electron withdrawing. To explain that, let's look at the intermediate that results from attacking that para position. I didn't need to move those bonds. So that's going to put a positive charge there. But it can also put positive charge on these two locations. Let me do them in order. So if you were to draw your triangle in the ring, right, it's putting it on every other carbon. This one, however, can also form a resonance structure that puts that positive charge out on the oxygen. And unless you have the positive charge on that, what we call the ipso position, you can't do this fourth resonance structure. So attack at the meta position would put the positive charge on these locations, the two ortho and the para, and never there, which means that fourth resonance structure would not be available to you. You could also have drawn resonance structures of the starting material and shown that it's the ortho and para positions that have the negative charge because of the resonance donation. So you can reach the same conclusion from looking at resonance structures of the starting material or from looking at resonance structures of the intermediate. That's not always true, but it's true when you actually have a lone pair on the outside atom. If you were explaining the ortho-para direction of just the CH3 group, right, there are no resonance structures of the starting material, you would have to draw these. And in that case, your argument would be that this positive charge is stabilized by hyperconjugation to the CH3 group, and that makes the positive charge more stable when it can get into that position. So that one's fairly straightforward. That was one of the ones I used as an example. This one's a 5-membered heterocycle. So it's activated relative to benzene. And the reason for that is that there are 6 electrons in the pi system, but they're shared among only 5 nuclei. Right? what we want to do is compare the 2 and the 3 position by looking at the intermediate that would result from attack at the 2 position and compare that to the intermediate that would result from attack at the 3 position. And what you'll find is that there are 3 resonance structures you can draw for this one. And only 2 resonance structures that you can draw for this one. So the ability to do that extra resonance structure makes the 2 position more favored, and the product after removal of this hydrogen will be that. All of the 5-membered ring heterocycles are more reactive than benzene. Thiophene is the least reactive of the 3 because this orbital overlap's not great. Whereas the 2 heterocycles that have a second row element, furan and pyrrole, have better orbital overlap. So in order of reactivity, it goes like this. I'll get to your question in a second. Where pyrrole is the most reactive. Furan is a little less reactive than pyrrole because oxygen is more electronegative, which means that it's hanging onto the electrons a little more tightly, making them less available. Both are more reactive than thiophene because the extra resonance structure with the double bond to the heteroatom is better when you have 2p overlap than when you have 2p3p. And they're all more reactive than benzene because those electrons are shared among fewer nuclei. Yeah?
I was going to, yes, the resonance structure, but regardless of that, wouldn't it also just be on the ortho? It could be on either side, obviously, because it's symmetrical. But would it be on the ortho more so than the meta because it's activating already? Aside from the resonance structure explanation as well.
There is no ortho and meta position on this one because there's no substitution on the ring, right?
Yeah.
Ortho refers to relative to the substitution. So I guess you could consider that to be the ortho position because it's next to the sulfur and that to be the meta position, but that's not a standard use of those terms. Those terms usually refer to a ring that's got something hanging off it rather than an atom in the ring. Like with pyridine, that's the 2, the 3, and the 4 position. They're not commonly referred to as ortho, meta, and para the way they would be if there was something here. So just nomenclature. If you want to be safe, don't use ortho, meta, and para, 2, 3, and 4, because that's always going to be true. So there's 2 things going on here. There's the activation of the ring because of the electrons being shared among fewer nuclei, and then there's the attack at the 2 position because of the additional resonance structure that's available with attack at the 2 position that's not available with attack at the 3 position. So now we've got one that actually has a 5-membered heterocycle and a benzene ring in it. That ring system is referred to as the indole ring system. Indole derivatives have a tendency to smell pretty bad. 2-methyl indole is called scatol for obvious reasons. So we have to decide which ring to attack, and then we have to decide what position to attack the ring. This, by the way, is on page 1159. It's exercise 25-14. So how did you approach this one? What did you do? This is the one that I didn't go over in class. the first thing to realize is that the 5-membered ring is activated relative to benzene for the same reason we just discussed, right? Six nuclei sharing the electrons in the left-hand ring, only 5 nuclei sharing the electrons in the right-hand ring. So now I have to decide whether I'm going to attack here in the 2 position or there in the 3 position. But it's a different ring system, so I can't just say, well, it's going to be the 2 position because it was for thiophene. Right? That may not be the case. So what I want to do is draw the intermediate for attacking in the 2 position. And in this case, it's SO3, so the intermediate looks like that. And draw the intermediate for attacking the 3 position. And then see what additional resonance structures are available to me. So if I attack in the 3 position, I can push that pair of electrons from the nitrogen form a double bond. Just going to write that as SO3 minus. And I still maintain the aromaticity in the benzene ring. So I have 2 resonance structures that maintain the aromaticity in the benzene ring. If I attack in the 2 position, the very next resonance structure I can draw will have broken the aromaticity in the benzene ring. And then I can draw more resonance structures. But I don't really need the additional resonance structures as soon as I realize that there's only one resonance form that can keep the benzene ring intact. So there are 5 resonance structures available, but this is the only one that has an intact aromatic ring over on the left. I can draw some more resonance structures for this one as well if I want to, but the key is these 2. So the 2 position is not favored in the indole ring because the extra benzene ring changes the stability of the whole system. You may, if you're a biochemistry type, notice that that indole ring is the side chain of the amino acid tryptophan. And the point of attachment of the CH2 group to the indole ring in the amino acid tryptophan is indeed at that 3 position, which makes sense. So even in the biological system, that 3 position is the reactive position. I think I might have that stereochemistry backwards. What's that? The SO3? Not in this case. Sulfuric acid can sometimes act as a dehydrating acid. Nitric acid is an oxidizing acid. Sulfuric acid is generally not an oxidizing agent.
That's
I mean, if you heat this up, yeah, the whole ring can potentially decompose because you can start protonating this nitrogen, but that nitrogen isn't really very acidic because this, or basic rather, because this lone pair is part of the aromatic ring. So normally, the indole and pyrrole, where you have that lone pair on the nitrogen as part of the ring, generally doesn't get protonated by the acid. And then the last one is this isoquinoline. And so we again have to decide which ring is going to be attacked. The presence of the nitrogen in the six-membered ring deactivates the ring. And in this case, what you're looking at is there are 6 atoms in each ring, but in the right-hand ring, the nitrogen has more protons in its nucleus, which means those electrons are going to be held more tightly. In the 5-membered ring, it's more reactive because there are fewer nuclei sharing the electrons. But in the 6-membered ring, there are the same number of nuclei sharing the electrons, just one of them is a bigger, a more positively charged nucleus. So the position of attack will be this ring. And then we have to decide where. So position 5, position 6, position 7, or position 8. We know that in the naphthalene system, it's these 2 positions that are favored. So 5 and 8 are favored over 6 and 7. And that's because there are 2 resonance structures for attack at either of those positions that maintain the aromaticity in the pyridine ring. Whereas attack at position 6 or 7, basically attack at position 6 or 7 immediately puts a positive charge next to the other ring, which means you're going to have to break that ring in order to generate the aromaticity. You can also draw a resonance structure for this, right, that has the double bonds in the opposite position. And that makes it more obvious that when you attack here, right, if you put a nitro group here, you're going to put the positive charge there. The next resonance structure is going to move that over and force you to break that ring. Right? And the same would be true for attack here. You'd put the positive charge there, and then the very next resonance structure would have to break the aromaticity in the next ring. So we're choosing between 5 and 8. Right, so that's my initial position of attack. Aromatic ring in the pyridine, if I draw it like this, right, in both these cases, intact aromatic ring there. There's going to be another one that allows me to move this one, right, or move this one. Those are the resonance structures that are not available for attack at position 6 or 7. You'll notice it doesn't matter whether I show the pyridine ring in this resonance form or this resonance form, I get the same conclusion. So now what we have to consider is where else that positive charge is going to go once it goes into the pyridine ring. And in this case, it's going to go here, and then it's going to go here, and then it's going to go there. Whereas in this case, it's going to go here, and then it's going to go here on the nitrogen, and then it's going to go there. So if you attack at position 8, one of the resonance structures that you're going to draw has a positive charge on that nitrogen. And it doesn't want to be on that nitrogen. It's only okay to put positive charge on nitrogen when you have a filled octet. And in this case, I don't have a filled octet on nitrogen. Right? So I've got nitrogen with only 4 electrons and not 4 electron groups. Don't want to put a positive charge on an electron deficient nitrogen like that. So this is a bad resonance structure, which deactivates that one. You also have the inductive effect. The nitrogen is closer to position 8 than it is to position 5. So it's inductively electron withdrawing, and that's a bigger effect at the closer proximity. So you've got 2 reasons why you'd like to go on 5 instead of 8. Inductively, 5 is further away, and by resonance, position 8 requires you to put a positive charge on the nitrogen, which is not where you want that positive charge. And both of those positions are better than 6 or 7 because of the extra resonance structure with an aromatic ring in the pyridine system. So you get good selectivity on the isoquinoline that you don't get on the quinoline, right? Because remember, in the quinoline case, your inductive effect and your resonance effect are in competition. Generally, when the 2 effects are in competition, the resonance effect wins. Let me save this separately.